Hello everyone and welcome to another EMS webinar. Our topic for today is non-destructive testing simulation inside EMS. Our focus is actually going to be on simulating eddy current testing methods in EMS. So before we start, let's have a look at the plan for our talk today. For those of you who are not familiar with the software, we're gonna do a short introduction to EMS and an overview of its solvers. Then we're going to talk briefly about eddy current testing and its fundamentals, and then we're going to show you how you can set up an eddy current study in EMS, and finally analyze the signal that you're going to obtain from EMS. We're going to wrap up this webinar by a short Q&A session, but if at any time during the presentation you have any question, feel free to type it in the chat box and I'll do my best to answer it at the end. So EMS is basically an electromagnetic simulation package that operates inside some 3D CAD environments, namely SolidWorks and Autodesk Inventor. Working with EMS allows you to keep using those powerful modeling tools without having to export anything to some other software, while turning those SolidWorks and Autodesk Inventor into powerful and accurate electromagnetic simulators. EMS has 6 solver study types, and those can be roughly divided into magnetic and electric solvers. There are 3 magnetic solvers: magnetostatic, AC magnetic, and transient magnetic. Magnetostatic solver allows you to analyze magnetic fields, forces, currents, and associated phenomena in a steady state mode. AC magnetic does that in a frequency domain, and transient magnetic analyzes and computes all those results in a time domain. Electrostatic solver and AC electric compute electric fields, while electrostatic does it in a steady state domain, while AC electric does it in a frequency domain. Finally, there is electric conduction mode, which allows you to compute current distributions and electric fields in a steady state domain as well. In addition to these 6 electromagnetic solver types, EMS also allows you to couple these electromagnetic results across different physical domains and perform a truly system-level analysis. You can, for example, associate an electrical circuit with a coil in EMS field study and analyze the overall circuit behavior. You can also use the electromagnetic losses from currents or eddy currents in the core, and use those losses coupled with EMS thermal study to compute the temperature rise in the system components. On the other hand, you can couple EMS force and torque results with SolidWorks motion and calculate dynamic response of your system in time domain. Electromagnetic forces and torques can be also coupled with EMS structural to compute deformation and mechanical stress on the components of your system. So eddy current testing is based upon the difference between eddy current distribution for 2 different positions of the probe. Basically, the eddy current distribution induced in the specimen is not going to be the same depending whether there is a flaw or a smooth, flawless domain beneath the probe. So eddy currents are a consequence of an AC magnetic field generated by the probe. So if a conductive material is in the presence of an external time-changing magnetic field, eddy currents will be distributed on the interior of that conductive material. However, due to the skin effect, the magnitude of those eddy currents will drop exponentially with the depth of the material. How deep those eddy currents can actually reach into the material depends on the frequency of the external field, material conductivity, and permeability. So that way, this depth of penetration is actually limiting the application of the limiting factor in the application of eddy current testing. It is mostly used in cases that do not require great depth of measurement, such as surface inspection, thickness inspection, conductivity measurement. However, the depth at which you are performing the measurement can be adjusted by changing the frequency of the excitation current. So presence of a flaw or some other discontinuities in the material, in the specimen, will be projected in the coil impedance. Eddy currents in the nearby material affect both real and imaginary components of the coil impedance. So, for example, if eddy currents have higher magnitude, which they will in those zones where there is no flaw in the material, the eddy current losses will be higher in the system, which will be affected through the change in the resistance in the effective resistance of the coil. At the same time, those eddy currents will generate a magnetic field, which for different positions of the probe can be different, and in turn will affect the initial field produced by the probe in different ways, which will be reflected through a different equivalent inductance of the probe. So if you manage somehow to catch this change in the coil impedance and to characterize it, you will be able to estimate for example, the depth of a crack or its position, size, etc. So the role of electromagnetic simulation softwares like EMS in this problem is to help you reconstruct the impedance profile for a few different probe positions. So now let me know how you can perform basically this virtual calibration of an eddy current sensor and calculate the coil impedance profile in EMS. So therefore, let us switch to SolidWorks, where we have a simple eddy current probe, which is basically a coil represented by this ring here, and a specimen, which is one copper plate with a dent in it, right beside the coil. In addition to these two parts, we also have an air box in this assembly. The air box is necessary to enable electromagnetic interaction between the coil and the plate, and to serve as a domain for magnetic fields to propagate throughout the surrounding volume. The position of the coil in this assembly is defined by basically two dimensions. First one is the lift off, which is a distance 1 under the mates, which defines the distance between the coil and the copper plate. And then a second important dimension defining the position of the coil is distance between the coil and the flaw, which is named distance 2 in this assembly. So if you want to analyze coil impedance for few different distances between the coil and the flaw, what you can do in EMS is take this dimension from SolidWorks assembly and right-click on it, and so by selecting this, first let me select this dimension, maybe even hide the plate. Right-click on it and select EMS, add dimension parameter. So this way, this dimension is going to be made available to EMS to parameterize over it and perform a series of electromagnetic analysis for few different positions of the coil. So now that we have briefly analyzed this assembly, let me move to the EMS Manager tab and define a new study. To do that, you right-click on the name of the assembly, select Study, and here is where we get to choose exact study type that we want to perform. So in this case, since we are dealing with an AC coil, we're going to select an AC magnetic study. And if we want to generate studies for few different positions of the coil, we're going to have to also check parameterization. Then finally, we define the exact frequency at which we want to excite the coil. Hit OK. And this is this way we get a basic EMS manager tree, which starts by material folder. So this is the first step in any EMS simulation. We need to define material for each part of the assembly. So first we right-click at the name of the parts and select Apply Material. For the airbox, we're going to go with the air from the material library. For the coil, we're going to apply copper from conductor material folder. For the plate, as you can see, plate is basically formed out of this part. The plate is basically formed out of two bodies. One of them forms actually the most of the part volume, and that's the plate, which is going to be made out of copper, and then the smaller part representing the dent, the flaw, is going to be made out of air. So we right-click at this smaller part and select air, and the larger part is going to get copper. So this way, all the materials are added to the study. So finally, we must tell EMS to compute eddy currents distributed on the plate. To do that, we right-click on this part and select Turn on Eddy Effects. So the next thing that we need to do is define the coil. To do that, you right-click on Coils and select Wound Coil, and then select the part you wish to use as a coil. The next thing is defining the cross-section area of this part, which is going to serve as the entry point for the current. So to do that, you right-click on this face, select Other to be able to select this hidden cross-section area. Since the current is going in circular orientation through the coil, we're going to select same as entry point for the exit port. So this is exactly the way that the path current is going to take through the coil. In General Properties tab, we define the current cross-section area, the wire cross-section area, and the number of turns for the coil. So we can type in a number of turns, wire cross-section area can define as gauge 30, and okay, so for these specific numbers, EMS is computing the fill factor, and it's saying that it's exceeding the value of 1. So this way you can see that this this combination of numbers is not going to work. So we can maybe reduce the number of turns to 75, and now it's fine. Finally, you have to select whether you want to have a current-driven coil or a voltage-driven coil. We can go with a current-driven coil and current magnitude of maybe 0.5 amp. Hit OK. This way, the coil is fully defined. If you remember, the depth of at which eddy effects penetrate the material is highly dependent on the frequency. So, which is very important in this simulation, because we need to keep in mind what is the value of this characteristic depth when defining the mesh size for the simulation. Because if mesh size is if mesh elements are too large, we're not going to be able to capture this decrease of the eddy current density with the depth of material. So for this specific frequency and conductivity of copper, the depth at which eddy currents penetrate this plate is about a couple of millimeters. So therefore, when defining mesh at this part, we need to apply a mesh control and keep the maximum element size at maybe 0.5 millimeter, or maybe even 1 millimeter would do, but it needs to be smaller than it needs to, you have to fit at least a couple of mesh elements in the penetration depth. So hit OK. Finally, now that we have defined material, coil, and mesh, we can go and define the parameterization. So to do that, you hit double-click Design Scenarios under the Parameterization folder, and select how many steps and what exactly values of this distance between the coil and the flaw you want to simulate. So we can maybe go with between 0, which would this distance would align the coil with the flaw, and maximum could be 21 with a step of 3, which we should produce about 9 steps in this parameterization study. Hit OK, and this is pretty much it. This is a fully defined parametric simulation in EMS. We can now simply right-click on the name of the study and hit Run. But instead of doing that, let me go to a predefined and pre-run study with same parameters, so that we don't waste our time waiting for the results. Once the results, once the study has been computed, we get this additional folder in the tree, which is the results folder, and under this folder we can see different field plots, as well as the results table that contains inductances, resistances, flux linkages, and other different parameters of the coil. The first thing we could do is have a look at magnetic flux density plot. Since the air part is hidden, we cannot see the full field results. So let me go back and bring the air domain back. So now, to have a look at the full field result inside this volume, what we need to do is right-click on the name of this plot and select clipping and then section clipping. And this way EMS is going to cut this volume under along one plane, one SolidWorks plane. We can select actually which one we want to use. So since most of the action in this assembly is going on along XZ plane, let me select that plane to cut the system. Uncheck inside out. Okay. Deselect section plane center not to obstruct the view. And as you can see, this is the magnetic flux density plot for the case, for the scenario 1. Let me bring back the model edges. So you can see this is the field distribution for the case where the probe is exactly above the flaw. If you want to see the field distribution for a different position of the coil, we go to edit definition, and under scenario we should select different one, and then EMS is going to show us the field distribution for the case where the probe is in a different position. There you go. If you want to analyze and have a look at results for different moment in the period of the current and field, since this is a frequency domain solution, we can select the exact phase at which we want to look at the results. There you go. So changing this is actually allowing you to observe both fields and eddy currents for few different for actually any phase angle. So now let's have a look actually at the eddy currents plot. Which is under the current density folder. Since we are mostly interested with the eddy currents at the plate, we have here defined this plot as a plot on selected entity and selected only the plate, only the specimen. And you can see how the eddy current distribution is different and changing for different positions of the probe. You can actually right click on this plot and select animate. Select animate versus scenario. So EMS is going to show you the eddy current distribution for each position of the probe. Another interesting plot could be the vector plot of eddy currents. To do that, select 3D vector plots, no clipping. And we're actually going to do the same thing in this plot, plot it only on the plate. Zoom in. You can also animate the eddy current distribution versus the phase angle. So you can see actually how is the eddy current in the plate changing in the period. Most of the coil impedance results are contained in the results table. Here you have inductance, flux linkage, impedance, resistance matrix, induced voltage, losses in the winding, in the core, etc. And you can actually plot these for each scenario and see how inductance and resistance and overall coil impedance are changing for a few different positions of the coil. What actually might be most interesting in this case is to compare these results with some reference values and see how does EMS compare with the reference data. So this is the coil inductance and resistance result compared with electromagnetic analysis methods problem number 15 data published by the CompuMag Society. You can see that the inductance and the resistance variation results actually match very well the EMS results for resistance and inductance match very well the reference data. You can see that as we are with the distance between the coil and the flaw is increasing, the inductance peaks at about 10 millimeters away from the flaw, which is pretty much expectable because the eddy currents are going to be the most obstructed at that distance of the probe center from the flaw, and since they're so much reduced at that position, the eddy currents, they are going to have the least effect on the coil flux, on the probe flux, therefore allowing the coil inductance to expand more and acquire higher effective value. At the same time, effective resistance of the probe is dropping down, which is also expected because, again, at about 10 millimeters distance of the probe from the flaw, the eddy currents are the least, as well as the losses associated with those eddy currents, resulting with an effective decrease in the coil resistance. Here again, the overall magnitude of the impedance and the phase angle of the impedance also match very well with the reference results. So this pretty much concludes the webinar on eddy current testing in EMS. I would like to thank you for your attention and invite you to have a look at some more NDT or some other simulation examples on our website, on our YouTube channel. If you're interested in trying EMS for yourselves, please contact us through this email address or phone number. Now I would like to see if there are any questions and if I could answer them. Well, okay. I would like to thank you for your attention and invite you to join us on the next EMS webinar, which should be in about 2 weeks. Thank you. Have a nice day. Bye-bye.